now comes our next speaker. Great. Let me just say a few words about our speaker, Fredrik Johansson. Fredrik is an assistant professor at Chalmers University of Technology, Sweden. Before joining Chalmers University of Technology, he was a postdoctoral researcher at MIT with David Sontag. And his research has been focused on advancing machine learning methods and causal methodology to improve decision-making with a lot of applications in healthcare. And actually, he has a very prosperous group in Sweden working at the intersection of machine learning, causality, and healthcare. So Fredrik, whenever you're ready, it's your time. Thank you for being with us today.
Well, first of all, thank you for inviting me. I think this is a great opportunity to see some very diverse, work on causal inference. I also want to thank the previous speaker, Sarah, for setting me up for this, because if anything, I'm even more causality inspired and sort of less causal inference focused here. But I think you'll find that it's interesting nonetheless. I think it's useful for causal inference, and the reverse. The causal inference is useful for machine learning here. So we'll see if you agree with me after the talk. So the setting for this work is a very simple prediction problem, essentially. So I think of this standard machine learning 101 prediction problem. We have some features that we want to use to make a prediction of some outcome. And this is just one example of the many that I've worked on previously. I'm sure you can think of 100 yourselves, but here we're curious about, for a new patient or subject who comes into a memory clinic or see their primary care physician, we might be curious to predict whether in 4 years they will progress into Alzheimer's disease if they've shown symptoms of cognitive decline before. And so this is just one example, again, of something happening in the future that we might be interested in predicting from the past. So we have some baseline features X1. We want to predict some outcome Y. But we might also think about a more causally related setting, if you like, where we want to predict the effect of some treatment. So now we have a treatable disease or condition, and we give a treatment A to some subject, and we want to know what is the effect of this treatment down the line. Perhaps we want to predict the outcomes that we would see under different treatments and which one of them we would prefer to give to the patient. And so, if we have certain conditions, we know that, for example, if the variables X1 that we collect are an adjustment set, we know that we can learn to predict the effects under different treatments in the setup. And a standard machine learning sort of follow-up to such an analysis would be to collect some data set where these X1s satisfy, say, exchangeability, ignorability, and then do empirical risk minimization to find a function which approximates well this outcome Y given the baseline covariance X1. So all I'm showing here on this slide is that a very common thing in machine learning is that we find hypotheses H hat here on the left by minimizing our empirical risk, which is just the average loss in predicting Y given X1. And so in this case, our data sets are just pairs of features X1 and outcomes Y. We have a bunch of those, and we hope that they're independent, and then we can sort of conclude that if these conditions hold, if we have enough samples, then eventually our empirical risk will be a good representation of the expected risk or the expected error we might make if we use this system for new data points. And of course, in this very simple setting, at test time, when we use the hypothesis that we learned, we only have access to the baseline features X1. So H hat, our hypothesis, is a function which takes X1 and produces some prediction of this outcome Y that we care about. And this hopefully doesn't sound strange to you. At test time, we don't have access to anything else than what we would like to show to the model, will give us input to the prediction. But what I want to talk about today is that at training time, if Y is in the future, if Y is some time separated from X1, it's very likely that we have more information collected along the way. We might have a scenario like this, where a training subject, shows up at a clinic, we follow them for, say, 4 years, and then after 4 years, we make a note of the outcome of their progression or of their treatment effect. But along the way, we saw them every 6 months or so, and we collected intermediate observations. In the context of Alzheimer's, this might be repeated tests of their cognition, just to see where they're going. And so what I'm saying here is that at training time, we have access to intermediate observations between the baseline and the outcome, which might be useful for learning. It won't be useful for prediction because we don't have access to it when we use our model, but it might be useful for learning. And so in the context of this, in this talk, we will call this intermediate data privileged information. And this is borrowing vocabulary from Vladimir Vapnik, who studied a setting where you have access to more than the main variables that you care about, your inputs and outputs, or inputs and targets. You have access to data just for learning, not for prediction. And so, yeah, our privileged information will be this intermediate time series. As I'm sure you can guess, or maybe you've already done this yourself, in a lot of standard machine learning applications, you will just discard this information in between because we want to predict y from x1. That's the goal that we're setting for ourselves. That's the problem we're trying to solve. So standard supervised learning will just make use of those pairs. We will use x1 and y for a number of different subjects or samples. And we forget that there was intermediate information. And of course, if we collect enough samples, if M is large enough, then we can get the kind of estimate that we want. This, just throwing away the privileged information, will still lead to consistent estimation. We can still get a good approximation that way. But surely it should be that these intermediate values are useful somehow. And of course, yes, it turns out that this is the case. This is an example that I'll expand a little bit on later. But the point will be that when we don't have so much data, when we're in a data poor domain where it's very hard for us to collect enough samples, the privileged information can lead to more efficient learning. And so what I'm showing you here is two plots, essentially, a gray one, which amounts to classical learning, where we use only the input and target, and the privileged learners, which use all of the data we have access to. They're using the same architecture, but what you can see is that the privileged learner is able to achieve the same performance, so measured in R squared here, as the classical one, using 60% fewer samples. So we can get huge efficiency gains, right? And so this is what we'll talk about today. How do we best make use of privileged information to get this kind of efficiency gain? And this can be useful for estimating causal effects, for example. But can we also prove that it will be useful a priori, or at least can we identify conditions where we should expect privileged learning to be preferable to classical learning? And here we'll use some assumptions inspired by causality instead. So to do this, we will need to define a few things. The first thing will be how we measure quality of a learning algorithm or a learner. And we will do that using the expected risk, no surprises there, but it's a double expectation in this case. So a learning algorithm will be a map from a data set, a random data set, to a hypothesis. And so the risk of the learning algorithm will be an expectation over both data sets and future points that we apply the output of the algorithm to. So R bar here being our expected risk for learning algorithm A, applied to random set D, and we take the expectation over those random data sets. Otherwise, the risk is the same as you are used to. And then we say that an efficient learner is one that, on average, outputs a hypothesis which has smaller risk than another learner or another algorithm using the same number of samples. So then you're more efficient. Okay, so as you might already have guessed, we will compare two classes of learners. There will be the classical learner, which uses only baseline time points or baseline information and outputs or targets. So the baseline information will represent what is used for prediction, what is used as input to the algorithm. And of course, y being the outcome that we're trying to predict. And then the privileged learners will make use of all the data we have access to. So an entire time series in our case of the baseline data and anything that happens leading up to the outcome that we care to predict. And our goal is to establish that a privileged learner is on average has smaller risk than a classical learner for the same size data set. This is what we mean by a privileged learner being useful. And of course, as almost always, we're not the first to think in these terms. And in fact, I already alluded to or referred to Vladimir Vapnik, who with co-authors have worked on this setting of learning using privileged information that's available to us for learning, but not for prediction. And so this LUPI, or learning using privileged information framework, was studied in a series of papers that you can find. I have some references at the bottom here. But one of the key ideas of that work was to try and establish that a privileged learner can achieve a quicker sample or a lower sample complexity than a classical learner. And so in a particular setting, they have been able to show that privileged learners can achieve fast rates, meaning that the error decays as 1 over m, where a classical learner could at best achieve a slow rate where the error decays as 1 over square root m. Now, the issue with that for our setting is that these are limited to very specialized constructions. So you can show that such examples exist, but it's very hard to generalize or generally apply this kind of analysis. So we're interested in something a little bit more broad. But additionally, these results kick in when the number of samples is already fairly large. But the whole point is that we want to work well in data poor domains. So M is not that large. Another related piece of work is that of surrogate learning. So in surrogate learning, the goal is to estimate causal effects more efficiently in cases where the outcome that you care about is not always observed. So a typical setting might be in a clinical trial. You might want to know whether the average sort of side effect rate is larger on the main treatment than on the controls. And of course, you won't know what the side effect rate is until you've measured it at your follow-up time. But then you might be able to use information that's collected during your trial, surrogate outcomes that can be helpful for making this prediction or for estimating the effect. And so you can show that asymptotically, yes, it will be useful to have these surrogate information in cases where your outcome are sometimes missing. But the existing results for this setting become uninformative for the type of question we are asking, which is it better to learn using privileged information or not? It becomes informative when you always observe the outcome. And that's the setting we're studying. So if you have the surrogate, you also have the outcome is our setting, if you compare it to surrogate learning. So it doesn't give us everything we want, basically. Now, a third piece of related work is that of estimating total causal effects in a general causal graph. So Grohl and Perkovich show that if you want to estimate the causal effect of X on Y in the context of this larger DAG, it's useful to make use of information between X and Y, like post-treatment data, if you like. The most efficient estimator in this setting will be something they refer to as recursive least squares, where you estimate this child of a node given its parents, where you make a recursive prediction. And so all of these three results that I've shown you before, they study essentially asymptotic settings, but we want to establish something for finite and small samples. So we need some other tools. So instead, we'll make assumptions on the causal structure of these variables. Of course, that was part of some of the previous approaches as well, but we'll also use a different theory. And what we'll say now is that we'll assume that the privileged information, these observations along the way between baseline and outcome, they will be Markov. And I'll show you what I mean in the next slide. So first, what is the simplest thing we can try? Well, let's say that all of our data is somehow related linearly. That's where we'll start. So our data generating process will be a linear Gaussian chain. There will be a number of variables, x1, x2, x3, x so on, until xt, and then there will be an outcome y, which is what we predict. All of the things in orange here, they will be privileged. We don't have the access to them for prediction. So at test time, we only have access to x1, but the things in orange might be useful for learning. we will assume that x2 is given as a linear function plus Gaussian noise of x1, or that's determined by x1 that way. x3 is determined by x2 that way, and so on. But we won't make any assumptions about the distribution of x1. That can be an arbitrary distribution. We also won't assume stationarity or homogeneity, I think some people call it here, meaning that the transition matrices from x1 to x2 and x2 and x3, they are different. So a1 and a2 will not be the same in general. Okay, so this is our setting. We're trying to prove that privileged information is useful, meaning we achieve a smaller expected risk using it than if we don't use it. And of course, we have to say what we mean by use it. And I will compare two very obvious learners. One classical learner, where you don't use the privileged information, you just use samples of x1 and y to learn a prediction of y from x1. And so we will call this a single step prediction because, well, for obvious reasons, you make a single prediction and that's your guess. So in the linear Gaussian case, I'm sure all of you know that an OLS estimate will be unbiased and it will be the smallest variance unbiased estimate. So that will be our classical learner here. So script AC, that's our classical algorithm. It takes a data set D and it outputs the OLS estimate. The privileged learner, which is supposed to make use of the data in between, will be in some ways the opposite of the classical learner. It will predict every step of this sequence, every step of this time series sequentially. So it will be similar to the recursive learner that I referred to a little bit previously. So for this, of course, we need to know the causal structure, or at least we need to know what information we should use to predict which variable and so on. And so since we're in a chain, that's rather easy at this point, but we'll talk about generalizations later on. So in the privileged learner, we estimate each transition matrix independently of each other. A hat 1 will be estimated using samples of x1 and x2, a hat 2 using x2 and x3, and so on. And for predictions, we just multiply all of these, rolling out the prediction from x1 to y sequentially. So the privileged learner will output the product of all the a's and the beta at the end. Both of these, of course, will be linear functions because we just have products of linear functions in the right-hand side. Both of them will be unbiased estimators of the true thing that we care about, the conditional expectation of y given x1. So the only difference between them will be sample efficiency, or, well, the only difference will be variance, I should say. Now, in this setup, we can show that if our data corresponds to our assumption, meaning x1 through xt and y, they are a linear Gaussian chain and they have isotropic noise, then the risk of the privileged learner will be upper bounded by the risk of the classical learners minus the expected variance of the classical learner given the privileged one. So notation-wise, this might be a little bit tough to look at. But essentially what you can think of is here that once we fix the output of the privileged algorithm, it might not be deterministic what the value is of the classical algorithm or what the output is. And so there's some variance in what the classical estimate would be when we fix the privileged estimate. If this variance is greater than 0, then we have a gap. Then privileged learning is strictly better. Of course, the variance cannot be negative, so we're never worse using the privileged estimate than the classical one. It might be a little bit surprising, this result, because the classic or the privileged learner fits t-1 transition matrices. So that's t-1 times d squared parameters plus just the vector of predictions at the end. So that's plus d. Whereas the classical estimator fits only d parameters. Yet we have better variance using the privileged learner. So this was some work that we did. Well, it says 2022, but we did it last year with my previous postdoc advisor, David Sontag and his group. The key step in proving this is using a so-called Rao-Blackwell technique. And specifically what that amounts to in our case is to show that the expected value of the classical estimate given the privileged estimate, or given the parameters that the privileged learner outputs, it will be equal to the privileged estimate. So the classical learner is essentially distributed around the privileged learner. When we establish that, then the theorem follows almost immediately. So this is just the main sort of work that we had to do. And of course, we use this empirically as well. We figured that in the original problem that we studied, or that I started this talk with, we were interested in predicting Alzheimer's progression, Alzheimer's disease progression, 4 years after some baseline time point. And that's what we looked at, among other things. So you can find more examples in the paper. And I illustrate here the efficiency gains that we get using the R2 score versus the number of training samples that we used to train these models. And so the blue lines in these plots will be classical learners. These are just your one-step linear regressions, or OLS regressions, I should say. The red line will be the privileged learner in the way that I described it. Black line will be the same as the red line, except we also assume that the transition matrices are the same at every time point. So we use all t-1 transitions to fit just a single matrix. And so we see here that both in the regression setting, where we're predicting a cognitive risk score called the MMSE, and where we're predicting AD diagnosis status, where we do a logistic regression at the last time step, in both cases, we consistently have higher R squared for the same number of samples. And the difference can be rather large when the number of samples is pretty small. So clearly here, in this example, privileged information is useful also empirically. Now, remember, we made a pretty big assumption, and that was that our system was a linear Gaussian chain. So we made both assumptions on causal structure, if you like, but also on the parametric class or function that we had to fit. So we would like to generalize that somehow. And what we settled on in the end for being able to reason about nonlinear functions is to look at a latent system. So in the first setting here at the top, we have this linear Gaussian chain where each transition is linear. We observe all of these variables, x1 through xt and y. In our second setting, we will think about a setting, we will think about a system that is partially unobserved to us, which is this z1 through zt. That will now be a linear system, but we won't actually observe that system. We will observe some nonlinear transformation of that system, if you like. So what we see here is that z1 emits some observation x1 through some nonlinear function psi, and there's an inverse function phi, which we would need to model or need to approximate in order to predict y, if we want to predict the entire way from x1 to y. So just like I said, we will assume that z1 through zt is linear Gaussian in the same way as before, but that the actual observations that we get are a nonlinear transformation of these. In general, this emission function won't be known to us, but we will also compare the classical setting where we see only x1 and y to where we have privileged information at each intermediate time step. So z2 emits x2, z3 emits x3, and so on. And we would like to have a very general result for this, but we have some work to do. So what we can show using a similar technique as before is that if we know something about this emission function, meaning we know its inverse up to a linear transform. So we don't know it completely, but we almost know it completely. We know this inverse function from x1 to z1 up to a linear transform, then the same result follows immediately. We will have the same exact guarantee. It's just that the setup is now generalized. We don't need to actually know phi. A kernel is enough. You can apply the same algorithm using a kernel, but it's still assuming more than we would like. So then we thought, okay, how can we reason about the case where you actually learn this phi, where you learn your representation function, which takes your observed data to the latent space? What can we do? And so since we had already established some results for kernel learning, we thought, okay, why not random features? They've been useful for kernel learning. And so that's what we looked at next. And so in this case, random feature embedding will be just some linear production with a random matrix, Wx, and then a nonlinearity applied to that. So this will cover things like random Fourier features, which you might remember from a while back, or random ReLU features where your representation is essentially a randomly initialized neural network, a single layer neural network, where you have a value activation. So you use that as your representation, and then you fit your model as you would have otherwise. So remember, we said that if we know phi, then we can proceed as we did before. We just map all of our x's to z, and then we use the same algorithms as previously. If we don't, in this case, we can use a random feature representation instead and use the same algorithm. And this is consistent in the sense that if we see enough samples, we can let our number of random features grow infinitely large. And that means that both our privileged algorithm and our classical algorithm will converge to what we want. It will be consistent asymptotically. It's not exactly the kind of result that we would like, because we want to say something for finite features, but at least it gives us some intuition that it's not insane to keep going with the random features, right? It shows us that at least it's in the right direction. Okay, so this is where we're at with the theory at this point. We've shown that something holds in the linear case, in the latent linear case, if you basically know the emission function, and then it holds in the infinite sample limit if you use random features. But we can do empirical work, right? So we tried also learning using random features. And the big point here now is that we're not restricted to linear systems anymore. So what I'm showing you this plot is kind of a lot, but I'll try to take you through it. So anything that's darker here, so black, for example, compared to gray, anything that's darker will be privileged and the lighter will be classical. So in this case, the black is below the gray, and we'll come back to that. Here we have a darker red, so that's using random value features, and the pale red or the pink will be a classical random value feature. And here we have the red on top of the pale, or the red on top of the pink. So why is the black below the gray? What does that mean? Well, it means in this case that using a privileged learner was worse than using a classical one. And why is that? Well, because the black is a linear estimator when applied in a nonlinear system. So this is the parallel of doing what we did before. We took a bunch of linear estimators and took the product of them to get our final prediction. And if all of those are biased, then the bias will compound. So doing linear privileged estimation might be worse than doing classical estimation if you're biased like this. Now, the blue group and the red group, those are both random feature representations, the blue being Fourier features and the red being value features. And in these cases, privileged learning wins for any sample size. So we see both a benefit of being nonlinear here, because the best nonlinear learner is much better than the best linear. But we also see a consistent benefit of using privileged information once you're not as biased. Of course, we can also do other things for learning this representation phi. So now we're making general nonlinear predictions using privileged information. And what is our sort of most common tool? Well, you can use a neural network of some kind. In this case, a classical learner might be just a feed-forward neural network where x1, your baseline features, are fed through some representation phi hat to z1, and then you make a linear prediction of y given x1. I'm saying classical here because we're not using x2 to xt, right? Our privileged learners will be all some variant of RNNs, let's say recurrent neural networks, because we will have some representation function which is applied at each time step. And then we will have various kinds of supervision to learn a good model of y. In particular, we will have supervision on predicting the next latent variable, z2 given x1 and so on, but also on predicting y. And we consider a few different variants of that, because the first thing that you might try, having read the linear case, doesn't actually work very well. I can't expand on that here, but that's what happens. So if we do this, we are able to fit things like images. So in this example, we have data that they look essentially like 2D images of clock faces. They rotate in time. And these images are representations of a 2D latent variable that we don't have access to. So our latent variables is a linear Gaussian system, like our theory wanted us to have. And our images are this image representation of these 2D variables. And also here we see that privileged learners, that's blue and red in this case up here, do better than classical learning, which is this gray line over there. Maybe I shouldn't paint over because they all look red. But this is the example that I showed you on the first slide. If we want to predict use as good as the best classical learner here, we can use 60% fewer samples if we have privileged information. That's what we saw in this case. So that was exciting for us. I'm going to have to wrap up, but my main takeaway from this work is that we shouldn't, of course, throw away privileged information. It's very useful to us. And in particular, we can, under certain assumptions, show that preference for privileged learners is independent of sample size. Now, the gap, the extent to which the preference holds, it varies with the number of samples, but preference holds regardless. And empirically, random features and learned features both work really well in the case where we have nonlinear functions that we're trying to learn. Now, there's a number of open questions with this work. Perhaps most importantly, we've assumed that we know, essentially, we know the parametric form of the things that we're dealing with. We have some infinite sample results for random features, but we would like to be able to generalize theorem 1 to the case where we have a finite number, or where we have regularization, because that actually works really well empirically too. We would like to be able to use a different framework or tool than Rao-Blackwell, because it actually forces us to reason about what the classical learner outputs as a function of the privileged one. And that's easy to do for OLS, but less so for other estimators. Now, maybe I'll just end by, by having a little pointer to the next talk here, because in some ways, what we would like is to not even assume something about the structure. For example, if we had a chain, but there's also a direct connection like this, could we handle that case as well? And so maybe this is a case for causal representation learning. At least we would like to be able to learn representations where we can provably be more efficient using privileged information. So look forward to the next talk. I think that will be about causal representation learning. I'm all out of time, so this was me, Fredrik. I have to thank my co-authors here, Bastian, Rickard, and Martin in particular, who have been master students with me, and then Zijan, Rahul, and David, who were my previous group at MIT. Thanks, everyone.
Great. Thank you very much, Fredrik. It's very informative. So let's take some quick questions. Okay.
Hi, Fredrik.
I have a quick, go ahead, please.
Okay. So hi, Fredrik. Thanks for the talk. I just have two general questions. So the first one, so I think in some real-world scenarios, how to measure or judge the privileged information is good or bad before using it. Because, you know, some bad PI informations might lead to a worse learner, right?
Yeah.
So that's the first question. The second one is, so how to connect the privileged informations, because is there some security issues here? Because you cannot leak the privileged information during the testing time, right? But in the models, it maybe involves some privileged informations. So you try to transfer the models to the new environments. How can prevent this kind of data leak or information leak?
All right. Thank you for the questions. So maybe I'll start with the second one. So it's not privileged in the security sense here. Privilege in this case just refers to the availability. At test time, it's not even produced yet. So it's privileged by time, if you like, that X2 through XT, they haven't happened yet. So I can't leak it. So it's a different notion of privilege than comes from the security domain. The first question, sorry, go ahead.
Yeah.
Oh, okay. The first question I think is very interesting because so you asked about, in practice, how do we know if the privileged information is useful? And first of all, you don't have to actually know in advance. Because you can do cross-validation. Since we're dealing with prediction problems here, we can see, does the privileged learner do better? And of course, that means that you have to maybe divide your sample to be able to tell, so you have a validation set. But what we found in the first paper, we have some experiments like that, where we show that it's actually, the benefit is large enough in some cases that you can actually sacrifice some data to pick between the privileged learner and the classical learner. You can also combine them. So what we show is that in the linear case, you can take a linear combination of your classical learner and privileged learner, and there's always some what do you call it, mixing strength that's better than either. Or at least not worse than both, let's say. And this we relate to distillation, which is also a related work where you learn from predicted labels or pseudo labels as well as your real labels. And you can show that those two things coincide in the linear case, actually. So yeah, have a look at the first paper for more discussion on the sort of practicality of this, I think.
Yeah, thank you.
Thank you.
Okay, great. Thanks to both of you. Actually, I have a quick one. By the way,
sure.
Next talk will be given by me. It's nice. Thanks to the organizers for kind of having my talk at the end. So this way we can make sure that the next session will start on time. So I will make my presentation shorter. Okay, so basically you are saying that by making use of something like a causal structure, right? You can really make better predictions, roughly speaking. And from another perspective, we can also say that right now you can see in deep learning, people try very hard to try different architecture, right? And how to tweak this structure in order to make better predictions. So eventually, the structure will contain or will give our insight into the underlying causal structure, even if the data is very complex, unstructured. Do you agree? Do you think that's sensible?
I think that's sensible. And I think, I mean, in our case, you can think of it as having additional sources of supervision for your architecture, right? And I think that's very, I think you're right that will be very useful. Now, of course, we have considered very, very simple architectures here. They're essentially feed-forward nets, and we haven't dealt with anything more fancy than that. But I think that general idea will transfer, that if you can build in more context into your system, it will generalize better generally.
Yeah, cool. But basically, a message might be that eventually, machine learning, deep learning, and the causality, the causal learning, may converge at some point. So that means it's clearly people can really benefit from, right? Or different research fields can really benefit from each other. Cool. Thank you very much.
So. Thank you.
Yeah, thanks, Fredrik. Yeah. Okay, now comes the next talk. Okay, let me. Could you allow me to share my screen? Oh, yes, I can. Okay, hello, everyone. So this is the last one. As you can see from the title, this is about advances in causal representation learning. And I would like to thank my collaborators, friends. So essentially, this is the result of a lot of efforts across different groups. So let me just give first of all, let me just give explain why we care about the causality. So first of all, all of you know the typical example to illustrate why we have to make use of a causal structure in order to do interventions, right? And why we have to make use of the causal information for treatments. And we also know, as you can see from the symptom paradox, right? In order to understand the data, in some situations, we have to introduce a selection variable and make use of selection, the way to deal with the selection bias. So this is a way to see the difference between the population and the sample, and provide a way to go back to the population from the sample you have. And furthermore, let me give some examples in machine learning. So first of all, you can see clearly, whenever you're faced with distribution shift, you may want to find a representation. And as Sarah just mentioned, it's related to causality, although in some situations, right, it may not be a causal representation, but it has some nice properties. I will explain it. And so for AI diagnosis and for recommended systems, clearly you care about the why. And the last example I gave yesterday illustrates that we have to find a way so that the machines and human beings actually learn and make use of the same set of high-level representations. In other words, so the representations used by the machines and those used by us should be consistent in some way. Then the question is, what kind of representation we use, right? So generally speaking, we make use of generative features or causal representations to explain the external world. Here you can see the difference between dependence and causality. I think here everyone knows that. We know that with the causal representation, generally speaking, is more informative, right? Because it can tell you the consequence of different ways to make changes, although the observations may be the same. Now the question is how we can learn the underlying causal structure or causal representation. I will explain what I mean by causal representation. So essentially, the problem seems to be kind of mysterious, right? Because in reality, we can only make use of data, and very often times we only have observational data without any interventions. And the goal is to recover the information of causality from such data. So then we have two problems to study. First, what kind of information or footprint of causality can we discover in the data, right? So we have to make sure the data reflects some kind of information of causality. And the second question is whether we can provide guarantees, essentially the identifiability guarantee. So regarding the first one, essentially we can make use of the so-called modularity property of the causal system. So modularity property says that if you have, say, different variables in the causal system, then their generating processes are not relevant to each other, although all variables in the system may be dependent, right? So the systems or the sub-processes are not related. And as you can see from this example here, we have a process to generate rain. We have a process to generate wet ground from rain, and another one to generate slippery ground from wet ground, right? So basically we have Z, X, and Y. We have causal model for each of them. Then the modularity condition says that those causal modules are not related. And then as the direct implication of this modularity condition, you can see several things. First of all, you can see conditional independent relations among the variables, although they may be dependent. And the second, you can see independent noise condition. So here E, the noise term would be independent from X, because basically they were involved in different modules. We know that the different modules are not related to each other. And furthermore, you can see that in non-stationary environments, we have minimal changes, because if you have for the causal system, the changes are not related to each other, right? So the number of changes must be minimal. For instance, here, if you have a change in the generating process of Z and another change in the generating process of Y, then any wrong representation or alternative representation will have at least two changes. So the causal representation will have a minimum number of changes. And furthermore, we know those changes are independent. So essentially, in causal representation learning or causal discovery, we just make use of such conditions because we can directly test those conditions in the data. Okay, the second problem is whether we have guarantees. So that means for causal structure learning or causal representation learning, we have to show that as we have enough data, the learned result is consistent with the underlying causal representation. So usually for each causal discovery method or causal representation learning method, we have such guarantees. By causal structure, by causal discovery, I mean the way or the task of recovering the underlying structure from data. And here the structure may have latent variables or latent confounders. And by causal representation learning here, I mean it as a subtask or sub-problem of a causal discovery. And with causal representation learning, we care more about the underlying latent variables and their relations, as you can see from some examples. So now we can just consider the whole problem of causal discovery and causal representation learning from the three, by making use of the three dimensions of the setting. So first, it's about what kind of data we have, right? In some cases, we only have data generated by a single distribution. In other words, we have ID data. But very oftentimes, kind of for intelligent systems, right, they can really see different kind of data. They see non-ID data, and they can make use of such data. And the second one is whether we can benefit from parametric constraints on the causal influence or causal mechanism. The last one is whether you can allow arbitrary latent confounders in the system. So on the right, I gave a summary, and now let me just briefly report some recent advances in this research field. So this is the first example. Here, the data were collected by Marlin Novak. So here you can see we have 8 features, and we have 250 data points. they wanted to see the causal relations among those features. And clearly, it's a very, very hard problem because first of all, we don't have temporal information. And second, we cannot really do intervention at all. And third of all, the relation can be very nonlinear, right? We have no idea about it. So in this case, at least we can make use of conditional independent relations. As you can see from here, this is how we can make use of conditional independent relation in the data to recover information of the causal structure. So here, let me just give an illustration of the PC algorithm. PC stands for Peter Clark. Basically, the method was developed by Peter Surrogate and Clark Limmer. So here we have data on the left, and then from data we can discover a set of independence or conditional independent relations, and then we would like to find a DAG or a direct acyclic graph or a set of DAGs to satisfy such constraints. If they are conditionally independent, then they are not adjacent. And then after that, we find a skeleton, and then we can find a V structure. V structure is unique because here, with V structure, we know that X2 and X4 are conditionally independent given X1, right? The condition set does not contain X3. That's why the directions will go to X3. And then we do orientation propagation to prevent fake V structures and the cycles and so on. So we see everything here. But clearly, we don't know the causal direction between X1 and X2 and the direction between X1 and X4. How can we get it? So later you can see how we can solve this problem. And second of all, in PC, we don't allow latent confounders. So if there are no latent confounders, and if faithfulness condition assumption holds true, then once you have enough data points, the result is correct. How can we deal with the confounders? So first of all, I will give some illustration regarding how we can recover those confounders, or whether we can really be sure that there are no latent confounder. By the way, this is the result by PC on the archaeology data. You can see from the data, we can really derive something, the causality, that is very informative. You can see from this picture. Now let's go further. So I'm going to give two examples to illustrate that even with only conditional independent relations, we can still say something about the confounders. Actually, this is a very small part of the algorithm of FCI, fast causal inference. So if you are interested, maybe you want to see the detailed FCI algorithm developed by Peter Surrogate in 1995, a long time ago. But this is one of the most universal method for causal discovery, although the result may not be very informative. Why? Because you have to show that the result is correct across all scenarios. As a consequence, it may not be very informative if you want to see whether a particular variable is a cause of some other variable. Okay, in the first example, so we have 4 variables, x1, 2, 3, 4, and you see a set of independent relations on the left. If you apply PC, you can get this result. So 1, 2 cause 3, and furthermore 3 cause 4. Now the question is whether it is possible at all for you to have a latent confounder behind x1 and x4, right? So this is a very difficult question because you only measure 4 variables. Now you like to see whether there could be latent confounders at all for 2 of the variables. Actually, the answer is no, because if you have such a confounder, then x1 and x4 will not be conditionally independent given x3, because generally speaking, they cannot be conditionally independent because they are deconnected given x3. So you can make use of this idea to solve a lot of problems, even including some our daily life problems, as you can see from here. X1 is rainy, x2 is wet ground, and x4 is slippery. Essentially, you can see the conditional independence between x1 and 4 given x3. And furthermore, if you know that x3 is not the cause of x4, then you know that 3 wet ground must be a cause of x4. And furthermore, you know there are no confounder. So it's very informative. Okay, now let's have a look at next example. Here, again, we have 4 variables. And if you apply PC, you see x1 is adjacent to 2, 2 is adjacent to 4, and that 4 is adjacent to 3. However, in this case, we know there must be confounders behind x2 and x4. Although we know they are dependent, right? Here, to explain this set of independent relations, we have to introduce confounders. Otherwise, you'll see some contradictions. Okay, and furthermore, we know that x1, 2, and x4 are not directly causally related, meaning that neither of them is a cause of the other. So all the dependence between X2 and X4 can be explained by the latent confounders. So similarly, you can see a lot of applications of this idea. For instance, let X1 be whether I'm sick, X2 be whether I'm in this meeting room, X4 be whether you are in this meeting room, and X3 be whether you are sick. Then you can see that conditional independent relations given the environment, so we have always a condition on something, right? And then you can conclude that although X2 and X4 actually happen at the same time, they are not directly causally related. We are here because of some latent variable. Essentially, we are here because we have this event. So here, with those two examples, you can see even with the conditional independent relations, we can say something about confounders. Now, I have a few minutes. We can go further. So even if you have two variables, if you are willing to make use of some rather weak assumptions on the causal mechanism, you can just distinguish between cause and effect. As you can see from here, the figures in the first row, in the wrong direction of the causal, in the wrong causal direction, the residual, the ultimate residual will not be independent from the predictor. While in the correct causal direction, the residual is independent from the predictor, as implied by the independent noise condition. So the same thing happened to nonlinear models, as you can see from here. So the post-nonlinear model is rather flexible, but we can still distinguish between cause and effect by making use of this model. Actually, there are only 5 situations in which cause and effect are symmetric. And those 5 situations are very specific. So we can say, generally speaking, even if we don't have temporal information, we can still distinguish between cause and effect for data generated by this very flexible model. Now let's go further. In many cases, the measured variables do not have causal relation in between. Instead, they were generated by some latent variables, right? So I always use this example in psychometric studies. You have answers scored to the questionnaire. Clearly, they are not directly causal related, but they are reflections of the underlying mental conditions. Mental conditions may be related. How can we solve this problem? So in the past years, actually in the past 15 years, a number of methods were produced aiming to deal with this problem. Here you can see application of some method we developed in recent years. This is the teacher burn-up data. So on this data set, basically the method given by computational, the result given by our computational method is almost the same as the hypothesis model by experts. So it's very cool, right? So computational method can really allow us to go beyond the data to recover the property. By the way, this experiment was done by Feng, who might be here. And we can go further. We can even recover kind of a deep structure with the latent variables. So here we have a number of measured variables, x1, 2, 3 through x11. And under some assumptions, we can recover all those latent variables and their relations. So for details, you may have a look at those references. Essentially, this problem is not completely done because here the assumptions are usually rather pretty strong. For instance, all methods assume that the causal influences are linear. Now let's go from the ID setting to non-ID setting. I have 2 minutes for this part. First of all, if you have only time delay causal relations in stationary environments, it's traditional time delay causality in time series, right? You may want to use granular causality or some extensions. And recently, we solved this problem. So as you can see from here, we measure variables, and the measured variables like image pixels in video data actually are nonlinear functions of the underlying latent causal processes, right? And then under very mild assumptions, we can recover all those latent processes, as you can see from those 2 very simple examples. In the first example, we have video dataset, right? As you can see from here. So with this video as input, we can recover 3 meaningful latent variables. Right here on the right, we have a second example. So here you can see the image, the video of 5 balls in different colors. Between, for some pairs of the balls, they have hidden spring in between. So with this video data as input, we can really recover those 5 balls and their relations. So we just take video data as input. And then you can go further. You can allow multiple distributions. So it's really important to see the connection between distribution shift and causal modeling. You know, causal models tell us how the joint distribution may change, implied by modularity condition. So we have more causal modules, those modules may change independently, right? So once we observe the data or observe the changes in the distribution of the data, we know, oh, there could be some causal model to explain such changes. And on the further assumptions, those representations will be causal. Even without those assumptions, those representations can provide a compact way to represent or to describe how the distribution can change. And then a lot of the prediction problems or prediction tasks can benefit from such a representation. So here, for causal discovery from non-station data, we can first of all find for which variables the causal mechanisms may change, and then can recover skeleton and the causal directions. And you can even find a way to represent the change in the causal influence. Okay, so I'll skip this example. And this has a direct implication in domain adaptation or transfer learning, as Sarah just explained. So, but this provides a kind of unified way to do domain adaptation. From the data sets, you can discover a compact representation for how the joint distribution may change, represented by this augmented graph. And then in the target domain, once you have data for the features, you can see domain adaptation is nothing but the problem of inference of the target variable y, given the values of the observed features according to this graphical representation. So the standard way to deal with the prediction in non-stationary environments. Of course, this representation might not be causal. Sarah also explained this point. Okay, I will skip the experiment results. Now, let me give a quick summary. First of all, it's possible to recover causality from the observational data. So causality is not that mysterious. Of course, usually in order to recover causality, we have to make rather strong assumptions, right? But even without that set of assumptions, the discovered representation could be very useful for predictions in non-station environments or complex environments. And second of all, those methods can be considered as the instantiations of, say, modularity condition. Basically, we make use of different levels of changes in the data. So you may make use of different values of the variables. So this is one level of the changes. And you may make use of the change in hidden variable parameters. Essentially, you make use of multiple distributions or heterogeneity. And finally, I would like to say that this is only the beginning of causal representation learning. In the long run, it's really essential to recover the latent variables, all those relevant latent variables and their relations with the identifiability conditions. There are so many scenarios to consider. Okay, so this concludes my presentation. We don't really have time for any question. So if you are interested or if you have questions, please just send me a message, send me an email. Thank you very much for being with us. So this is the end of this session. Thank you very much, everyone.